Hello everyone, welcome to our other class where we will do problems from this section 5.2. Okay, now this section is a section where we do mainly finding the volume of solid that is generated by revolving around an axis. So this method, washer method, while toward the end we will work on some problems where we basically do the integration of the cross section, okay, which is the basis of the disc and washer method. Okay, now let's start with question number 2. Here we have a solid obtained by revolving the shaded region about the specified line about x-axis. We already have the graph, which is one of the big issue later on. What if we don't have the graph? Okay, now if we have the graph, then what we do, right? So let's see. We have that function. Hold on, I need to fix something. Give me a second. I just realized my number 4 is not a complete question. It should look like this. Okay, so number 2 here we have the curve or the above that is square root of x. The curve below is 1/2 x, and then later on we will generate by revolving this with respect to x-axis, right? So the red curve will be continued this way later on, and then the blue one will be continued approximately like this later on. The region generated will be, I try to match the color, will be like this, right? And revolve about the x-axis. So that's what it looks like later on. Okay, now the thing is, if we have a cross section, about that solid, notice that the cross section is perpendicular to the axis of the rotation. It's not a good one. Okay, now this typical line here, when we rotate that with respect to the axis of rotation, I hope you can see that we have a ring approximately, right? A ring. Now that ring has outer radius. The outer radius of that ring is from that axis of rotation to square root of x. You see, right? That's the outer ring. You know what? I think it's easier for us to see if I mark it this way. This is the radius of the outer ring. From here to the axis of rotation, that's square root of x, right? So the big radius is square root of x, while the smaller radius, yeah, why I keep going? I have a hard time. Yeah. Well, the smaller radius is the one here, which is y equals to 1/2 of x. So the smaller radius is 1/2 of x. Okay, so yes, the procedure will be start from the graph, which they already give us, and then rotate the typical line. This is the typical line here. This is the typical line here. When you rotate that, you'll see a ring, right? So from there we generate what is the area function. The area function will be the area of the big circle minus the area of the small circle. Is it right? And then that is equals to pi. You know what? Let me factor the pi out right away. And then r, capital R squared, that's x. And lowercase r being squared, that's 1/4 x squared. Okay? Or you can just do it next to it. This is pi times square root of x being squared minus pi times 1/2 of x being squared, right? Okay, and then when you factor out, that's what you see. Now, once it is in simplified form, then the volume will then be integral. They intersect at x equals to 4. Thomas, how do you know x equals to 4? Here. They actually give it to us. Okay, from x equals to 0 to x equals to 4. Okay, pi is the coefficient, let me pull it out, of x minus 1/4 x squared dx. Okay, that's the setup. And then from there, just integrate. You integrate it yourself. Okay, I will not do the integration anymore. I assume everyone at this point should be able to do that kind of simple integration. Okay, that's for number 2. Let's go on with number 4. I think I don't want to draw the line there because here we will rotate about, revolve about y-axis. So because I revolve about y-axis, then when we use washer or this method, if the axis of rotation in this case is y-axis, why I cannot really draw a straight line today. If the axis of rotation is a y-axis, then the typical line has to be perpendicular to it. Okay, the typical line has to be perpendicular to that y-axis, the axis of rotation. Okay, now then I will rotate this segment here. It becomes like this, approximately. Okay, which if we make it facing us, then this will be the big radius here from y-axis to this part here. Do you see that? Okay, that is the big radius, which is y equals to x over 2, but because we integrate with respect to y later on, we need to solve this in terms of y. So this becomes x equals to 2y. Is it okay? The radius, big radius here will be 2y, while the smaller radius that's from here to here. Take a look. That's the smaller radius. That's y equals to 2 over x. But again, because we will integrate with respect to y this way, then we need to solve this as a function of y. Okay, this will be xy equals to 2, so x equals to 2 over y. So the shorter radius will be r equals to 2 over y. Okay, now again, if you get a bit confused, feel free to pause the video and then play it back a little bit. Okay, I erased this so that our graph does not get too complicated, you know. So our area function of y is now becomes pi big R squared minus pi small r squared. Okay, that's pi times 2y squared minus pi times 2 over y squared. If I factor the pi, I will get 4y squared minus 4y to the negative 2. That's our area function as a function of y. Actually, if you notice, I can factor another 4, huh? Well, I will just leave it there for now. Okay, so the volume then becomes, integral of pi times 4y squared. Pi is just a coefficient, so I can pull it out from the integration. Okay, likewise, if you want to pull the 4 out, go ahead. Let me just do that. Let me pull the 4 out. So I factor the 4 out as well. Okay, so the integral will look like this, but we have problem. What is the domain of integration? From what number to what number? Okay. Notice that we integrate this with respect to y, right? So we will need to look at the y of this coordinate here, which is 1. Do you see that? Okay, it will start from 1 to the y of this line here, which is 2. Okay, so we will integrate from 1 to 2. Basically, the limits of integration. Let me erase this so that we can see better. I hope you can see better now. Okay, that the y value of the interval of integration is from 1 to y equals to 2 here. We look at the y. Is it okay? Now let me draw back that typical line segment which we rotate. Okay, now again, I hope and I believe you should be able to integrate that yourself. Okay, let's go on to the next question. In number 12 to 28, sketch the region and then the solid and the typical disk of ore washer. Okay, so the challenge here is like they don't give us the graph, we need to graph it ourselves. Okay, the assumption is you have some pretty solid foundation in pre-calculus such that you are able to graph some basic function fast. Okay, so for example here y equals to 1 over x, that's a hyperbola, right? It's supposed to look like this. Okay, it's supposed to look like that. Now, in my class, I actually emphasize on the first week or at most the second week of class that students should be able to graph this fast. So one of the coordinates 1, 1, 2, 1 half, 3, 1 third, 1 half, 2, 1 third, 3. So that's the graph. In the first quadrant only I will do here. Okay, because from the graph I have from the restriction I see y equals to 0 is x-axis. Okay, x equals to 1. Let me draw it here. X equals 1 is like this here. This is x equals to 1. And x equals to 4. Let's say it's approximately here. Okay, this is y equals to 1 over x. Now, the typical line segment we have will be this guy, which if I rotate, it gives me a disk, right? That disk is very small, I know. Okay, but that disk will have radius. How high it goes from x-axis? It goes as far as 1 over x, right? Okay, so the solid later on will look like this. That's way too big actually. And kind of like that. Okay, but the typical, if you do the cross-sectional the cross section, it will look like a circle, a disc like this with radius 1 over x. So the area of that disc will be pi radius squared. Or we can write that as pi x to the negative 2 so that we can integrate that easier later on. Okay, now consequently, the volume will be integral of pi x to the negative 2 dx. Then take a look on the interval of integration. We will integrate from, they actually tell us here, right? They tell us from x equals to 1 to x equals to 4, right? From x equals to 1 to x equals to 4. So that's what the limits of integration. Okay? That's for number 12. Would you be able to integrate that yourself? Should be, right? You should be able to do it yourself. Okay, let's see number 14. You have y equals to square root of 25 minus x squared. This implies the y is non-negative, first of all, right? Because y is a square root. But if you go further, if you don't know what it looks like, play around. That's y squared equals to 25 minus x squared. This is x squared plus y squared equals to 25. So it is actually a circle with radius 5, right? It is a circle with radius 5, but we only take the portion where the y is positive, non-negative to be more precise. Okay, so we will take the portion where the y is non-negative. Okay, supposed to look like this, right? Supposed to look like this. Supposed to be like this, like a full circle, but we saw earlier the y is, by definition, square root is the positive branch, right? For square root. Now, we want this region is bounded by y equals to 0, which is the x-axis, right? That's y equals to 0. X equals to 2. To x equals to 4. Oh, okay. So that's our region, huh? Let me highlight that. This is our region. Now then, I pick a typical line which I will rotate with respect to x-axis. That's what they say, right? Rotate with respect to x-axis. Now that will give me this. That's not a nice this. That will give me a disc with radius. This radius here. This radius here is square root of 25 minus x squared. Okay. The solid later on, after we revolve that, will look like approximately like this. So the solid will look approximately like this. It's just like if you have a ball, but you take only part of that. It's kind of hard to imagine, huh? There's too many lines there. Too many lines there. Let me redraw this part. So this is the typical slice, which gives us this green disc here. Now, the area of that disc now will be pi r squared, which is pi times 25 minus x squared, because the square root cancels the square, right? Now, consequently, the volume is integral. They tell us the x is moving from 2 to 4, right? So this 2 to 4 I factor the pi out, and then the integrand is 25 minus x squared dx. Okay, so always sketch the domain first. You actually don't really need to rotate that if you don't want to, because it may be like too much stuff there at once, right? Okay, but at least you rotate that typical line. Okay, so that you can see, oh, that's actually a disk. So what is the area of that disk? Now, then from there you integrate. Okay, let me go further. Let me push this up here so that we save some space. Number 20, we have these two functions about y-axis. What they look like? So x equals to 2 minus x squared. So if we have y equals to 2 minus x squared, it looks like this. The vertex is 2. But now if we reverse the x becomes y becomes x, what it looks like? Then the y-axis, y-intercept now becomes the x-intercept. Is it okay? And then it opens to the left. So this is the graph of, maybe too big. You know what? Let me do this. So this is my scale. Approximately it looks like this. This is the graph of x equals to 2 minus y squared, and then x equals to y to the fourth. X equals to y to the fourth will be like this. Then I'm guessing, I'm doing a very big guessing, but then I will revolve this with respect to y-axis. So later on, my typical, because I revolved that with respect to the y-axis, let me say this again. The axis of rotation is very important for us to observe which method to use later on. But because I revolve with respect to y-axis, then if I need to use this method or washer method in this case, then the typical line has to be perpendicular. The typical line has to be perpendicular to that axis of rotation, okay, or that axis of revolution. Now, if I rotate that, oops, that's way too thick. If I rotate that, I will get something that looks like this. Okay. Now, let's, this is y equals to, I'm sorry, x equals to y to the fourth. X equals to y to the fourth. Okay, so if we draw the circles, the disk, one of them is the big disk, like this, right? With this radius from here to here. The radius is x, which is 2 minus y squared. You see that? From here you go to here, but this is part of this parabola, right? So the radius is, what happened? The big radius is 2 minus y squared, while the small radius, this one here, the small radius has radius of x equals to y fourth. So the small radius, let me keep it the same color. The small radius is r equals to y to the fourth. Okay, so the area of the region, it's a disk, it's a washer, right? It's the washer. I hope you can see that. This is the typical line. This is the typical line here. That's the typical line. When you rotate, you get a washer or a ring. Therefore, the area as a function of y will be the area of the big radius, the big circle minus the area of the small circle. That is pi times 2 minus y squared being squared minus pi times y to the fourth being squared. If I factor the pi, I will get 2 minus y squared being squared minus y to the eighth. You know what? Let me simplify this before. Let's simplify this before we actually end up with the integration. Okay? So this is pi times 4 minus 4y squared plus y to the fourth minus y to the eighth. So the volume will then be pi integral from of 4 minus 4y squared plus y to the fourth minus y to the eighth dy. But we have issue here. How about the limits of integration? We need to solve this. We need to find the intersection here and the intersection here. Where do these functions actually intersect? Okay, so x equals to 2 minus y squared, which is equals to y to the fourth. So 0 equals to y to the fourth minus y squared minus 2. Let me move this a little bit to the left. And if you try to factor this, think of that as the y squared. So y squared plus 1 minus 2. Okay, so y squared equals to -1. Of course, that doesn't apply, will not happen. Or n y squared equals to 2, or y equals to plus minus 2. Okay, so if we draw the limits of the integration, this is y equals to radical 2, and this is when y equals to negative radical 2. Okay, that's what I do there. If you can do that limits of integration first, that will be best. I honestly forgot to do it earlier. Negative radical 2 to positive radical 2. Okay, let me check my computation. I think I did it right. Okay. Too bad I'm doing this by myself, but if I have any student here, then that students can ask me questions. But you see the procedure. Sketch the region first, draw the typical line, okay, and then rotate that with respect to the axis of rotation. Then you see the washer, okay, or the ring. Then take a look what is the larger radius, smaller radius, so that we can get the area function of that ring, right, or that washer. Simplify first before you put them into integration. Okay, that's for number 20. Number 22, this is actually quite new. Number 22, we have a region bounded by y equals to x cubed. Let me make it a bit bigger. Y equals to x cubed looks like this. It looks like this. Y equals to x cubed, and y equals to 1. Y equals to 1. And y equals to 3. Okay. So this is the region, huh? This is the region. Am I right? Oh, I'm sorry. No, not y equals to 3. I did it wrong. My bad. X equals to 2. My bad. X equals to 2. X equals to 2. This is x equals to 1. So x equals to 2 should be here. So x equals to 2. This is x equals to 1. So we are talking about this region. Oh, okay. Good. So we have that region. Now then the typical line will be this guy, right? But we will rotate with respect to y equals to -3. Y equals to -3 is here. This is y equals to -3. That's the axis of rotation. So if I rotate this, actually, I'm sorry, I didn't look at the scale. Y equals to -3 supposed to look, it's supposed to be here, like 3 units down the x-axis, right? So this typical line segment here, if I rotate with respect to y equals to -3, it will look like this. Oh, that's a big ring, huh? It's a big ring. Then let's see, what is the big radius? The big radius will be from here to here, right? Okay, but we know this part here is 3 units and this part here is x cubed. Okay, so if we draw that big circle, let's say next to it, no, I just make it oval, okay, so that it doesn't take too much space. The big circle and then a smaller circle. Now notice that the big radius is 3 plus x cubed. Okay, again, the first 3 is basically the distance of y from y equals to -3 to y equals to 0, which is the x-axis. And then from x-axis to that part here is x cubed. Okay, so that's the bigger radius. Now let's see the smaller radius is 3 plus, oh, this is 1, huh? This is always 1. The y equals to 1, right? So the small radius will be just 4. Correct? The small radius will be just 4. The small radius will be 4. So the area of cross section as a function of x will be pi times the big radius. Don't forget to square it. Okay, this morning I have a student came to my office and asked me to check her work, and I myself missed it first time. And then it turns out that both of us both of us forget to square that radius. Yeah. Minus the radius of the smaller circle, which is pi 4 squared. Factor the pi, and let me FOIL that at the same time. That will be 9 plus 6x cubed plus x to the 6 minus 16. So that will be, actually it looks like this if you want to see that better. So that will be x to the 6 plus 6x cubed minus 7. Okay, that's the area of cross-section area as a function of x. So that the volume, if you rotate this yellow region here with respect to y equals to -3, the volume of the solid will be integral pi times x to the 6 plus 6x cubed minus 7 dx. The limits of integration is from 1 to 2. Okay, now again, I don't go with the integration, but it is assumed that you are able to do it on your own. Okay, so that you see the two, let me split that a bit further. Let me box it here. Let's do more. Number 24. we have y equals to sine x and y equals to cosine x. You really need to know this. Okay. Yes, we don't see it that often, but I still expect my student to be able to do it. Okay. So sine x looks like this, right? That's up to pi. Cosine x looks like this. And this is pi over 2. Yeah, actually you don't need to draw that far. We just need to see where they intersect. Okay. And oh, hold on. Y equals to sine x, y equals to cosine x. From 0, x equals to 0 to x equals to pi over 4. Okay, so it must be this one here. But let's confirm that they do intersect at pi over 4. Okay, y equals to sine x and y equals to cosine x. So tangent x equals to 1. So x is pi over 4 plus constant multiple of pi. But since we know it is in the first quadrant, then we just use the angle in the first quadrant. Okay, so this is pi over 4 here. Now we will revolve this with respect to, so this is y equals to cosine x. This is y equals to sine x. Draw a typical line. Revolve that with respect to y equals to negative 1. Let's say y equals to negative 1. Let's say it's here. Okay, so that typical line, when we revolve or rotate with respect to that y equals to negative 1, it will look like this ring then. Okay, we have a bigger ring, a bigger circle, smaller circle. Let's take a look at the radius. Let me use a thicker pen. The distance here is 1, right? Because this is y equals to negative 1. That's y equals to negative 1. So the distance here is 1 plus the bigger radius. For the bigger radius, I need to go that far, which is cosine x. I'm sorry. So the bigger radius is 1 plus cosine x, while the smaller radius, actually I don't need to erase that. While the smaller radius is 1 plus sine x, right? That's the smaller radius. I ran out of color. So this is 1 plus sine x. So the area of the cross section as a function of x will be pi r squared minus pi smaller radius squared. You can skip that actually if you want to. Is pi times, I factor the pi, capital R squared is 1 plus cosine x being squared minus 1 plus sine x being squared. Okay, then we get, if I FOIL that, 1 plus 2 cosine x plus cosine x squared x minus 1 plus 2 sine x plus sine squared x. This question, I need to show you the integration for this. Let me move this a bit lower because I need that space for the other question later on. Oops, I have something else underneath. This will be, notice the 1 cancels, right? The 1 cancels. 1 minus 1 cancels, so I get 2 cosine x minus 2 sine x plus cosine squared x minus sine squared x, which I think you don't know how to integrate that yet. But I hope you remember from trigonometry that cosine squared x minus sine squared x is that's cosine 2x. Otherwise, it's not integrable for your level yet. Then later on, let's see. So the volume will be, I factor the pi out, integral from 0 to pi over 4, right? From 0 to pi over 4. And then I get 2 cosine x minus 2 sine x plus cosine 2x dx. Okay? You know what? For this one, let me integrate that. So this will be pi times integral of 2 cosine x is 2 sine x, integral of negative 2 sine x is plus 2 cosine x. That's between 0 to pi over 4. The thing is, the last part, I need to do integration by substitution. 0 to pi over 4 of I do it later. Cosine of 2x dx. This will be pi times, let me separate that. So this will be 2 sine pi over 4, that's radical 2 over 2, plus 2 cosine pi over 4, that's also 2, radical 2 over 2, minus, when it is 0, that 2 times 0 plus 2 times 1, okay, and then plus this integral here will be pi times, let me do u substitution, u equals to 2x, so du is 2 dx. Okay, the limits of integration should change also. That will be from 0 to pi over 2 of cosine u du over 2. Is it okay? Or should I write it in full? I write it in full. I write it in full because I kind of like skipping some details step there. So what happened is I do the limits. I need to substitute the limits of integration also, right? That's 0, and u at pi over 4 becomes pi over 2. Now because du is 2 dx, so dx will be substituted by du over 2. Okay, long time no see, huh? Okay, so then here we will get pi times this part will be 2 square root of 2 minus 1 plus this guy is pi over 2. Actually, if you integrate that, you will get that's equals to 1. Okay, so this is 2 radical 2 times pi minus pi plus pi over 2. It should be 2 radical 2 pi minus pi over 2. So that's the volume of the solid. This integration, I think if you forget to convert this part, I think it's not doable for you at this point. So you have to remember this one. Okay, now then when we do the integration, the first two terms already integrable, so you just separate that, okay, from the parts that you cannot do directly because you need to do substitution first. Okay, that's for this number 24. It's kind of difficult, huh? I know, but be patient when you do that. Okay, you know what? I think I want to rearrange this to be more reasonable to do. Let me get this. Let me take this off here and then we'll do it underneath here so that I can move this guy. I try to save some space. I can move this guy to the right here. Okay, and then I can move this guy up. Okay, so this is actually the, once you get the volume, the area cross section, then you go to the volume, integral for the volume. That's for number 24. Let's see number 20. Let's see number 26. So we have y equals to x squared. Well, we know that. We know what it looks like. Y equals to x squared looks like this. And x equals to y squared. Oh, x equals to y squared looks like this. Okay? So this is x equals to y squared, while this one is y equals to x squared. Now you will see that they intersect actually at x equals to 1, y equals to 1. Now, if I rotate with respect to x equals to -1, let me erase this so that it don't distract us. X equals to -1 is somewhere around here. Let me just draw it here. And our typical line perpendicular to that axis will be something like this. So that when I rotate, it gives me this ring. Now, let's see that ring. The bigger radius minus the smaller radius. Okay, this is the bigger radius here, from here to here. Notice that the distance, because this is x equals to -1, so the distance here is 1, plus the distance here will be y equals to x squared. But I need that, we will integrate with respect to y, so then I need to rewrite that as x equals to y to the 1/2. Okay, so the bigger radius here will be 1 plus y to the 1/2. Okay, the smaller radius is from here to here, this part. I hope you can see that, which is 1 plus y squared, right? So the smaller radius is 1 plus y squared. Yeah. This is the small radius here, which is, if I repeat, that's the 1 unit here plus y squared. Okay, 1 unit from x equals to -1 to the y-axis, that's 1 unit. Then from the y-axis to the curve to the left is y squared. Okay, let me erase all of this so that it doesn't distract us. Sometimes we draw too much details, it's we get confused ourselves. Erase this part here. So the area of that ring as a function of y will be pi r squared minus pi small r squared. That is, if I factor pi, I will get 1 plus y to the 1/2 squared minus 1 plus y squared to the square. That is pi times 1 plus 2y to the 1/2 plus y minus 1 plus 2y squared plus y to the 4th. I know some of you may say, but Thomas, that's a bit too fast. I'm sorry, you are in Calc 1, right? At the end of Calc 1. Expanding that binomial, the square of a plus b squared, should be something you can do quite fast already. Okay, so pi, if you combine like terms there, you will get times negative y to the fourth minus 2y squared plus y plus 2y to the 1/2, and the ones cancels. Okay, now as you can see, the y will move from 0 to 1, so the volume will be pi times integral 0 to 1 of negative y to the fourth minus 2y squared plus y plus 2y to the 1/2 dy. Okay, I hope you can see, you can integrate it yourself. Okay, it should be doable easily, right? Okay, let me start with the next question. Number 66 and on, there are 3 more questions. Are cases where the cross section is not a disc or washer. In fact, let's read number 66. The base of this solid S is a circular disc. Let me emphasize that. It looks like, yeah, it looks like this. This is the disc here. I hope you can see that. That's the disc. If I highlight that, the disc will be this one. This is the disc. I hope you can now see that. Okay, that's the disc. Okay, so if we see from above, if we see this solid from above, it's actually a circle with radius r. That is a circle with radius r. Okay, the circle with radius r. So the equation must be x squared plus y squared equals to r squared. Now, it says that the parallel cross-section perpendicular to the base is a square. In other words, if I do the cross-section here, if I do the cross-section for a typical x, okay, I will get a square. What square are you seeing, Thomas? It's this one here. If I pick one of the cross-section, it will be this square here. Okay, that square. Maybe let me do it this way. So if I pick one of the square, this will be one of the, this will be the base. No, not that one. This guy pair with this guy. And then the square will be this one. That's the square. Okay, now the thing is, once this is the square, the x, then the height here will be square root of r squared minus x squared, right? But the square that we are talking about, the square that we are talking about, let me do it here. The square that we are talking about only has that square root of r squared minus x squared as half of the, that's only half of the side. Okay, so the full side will be twice of that, right? 2 times square root of r squared minus x squared. Can you follow me? This section that we're talking about here, this part here, is only half of that. The side, half of the side. Okay, so if you want the full side of that square, then it has to be double of that. Okay, should be double that. So this guy is 2 square root of r squared minus x squared. Now then, the area of that cross section as a function of x will be, it's not pi anymore, no more. That's a square. What is the area of a square? The area of a square is the sides being square, which will give us 4 times r squared minus x squared. Okay, now what is the volume of this solid then? It will be 4 times integral of r squared minus x squared. That's the area function of the square, right? From negative r to positive r. Okay, because the radius, the domain of integration starts from here to there, from negative r to positive r. Now, to make our computation a lot easier later on, notice that the integrand is actually an even function. And the domain of integration are opposite numbers. So we can fold it. Okay, what I mean by folding is this is 2 times, I keep the 4 there. I keep the 4 here. Okay, but this integral now, oops, let me change the color. This integral now becomes 2 times integral from 0 to r of that integrand. Okay, you can only do this if the integrand is an even function over an opposite domain. Other than that, the answer is no, you cannot do that. Okay, now to compute this further, this will be 8 times r squared x minus 1/3 r cubed from 0 to r. That will be 8 times r cubed minus 1 cubed. I'm sorry, this is x. This is supposed to be x. 1/3 r cubed. Okay. That will be 16 over 3 r cubed. Okay. So yes, we look at the domain and then get the side of that square so that we can find the area of that square as a function of x. Then we integrate that. Okay, let's go on with number 68. Base of this solid S is a triangular region with vertices 0, 0, 1, 0, 0, 1. 0, 0, 1, 0, 0, 1. Okay, so this is the base. Okay, the cross section perpendicular to the y-axis. Oh, they want y-axis right now. The cross section perpendicular to y-axis will be an equilateral triangle. So if I pull that typical line out, I will get equilateral triangle. Okay, now what is the equation of this line? What is the equation of this line here? I hope you can find that this is y equals to y minus x. The y-intercept is 0, 1, the slope is negative 1. Right? Or because we will do that with, we will integrate with respect to y later on, we can rewrite this as x equals to 1 minus y. Okay, so for a particular y, the length here is 1 minus x. Yeah, the length here is 1 minus x. You know what? If I choose a y, this is, I'm sorry, 1 minus y. Yeah, 1 minus y. That's the length. Okay? But I need the height though. I need the height. What is the height of an equilateral triangle? So let me redraw it even bigger so that we can see better. Okay, if this is 60 degrees, it's equilateral triangle, so the angles is 60 degrees. Now this will be 1 minus y over 2. Okay, and therefore the opposite side will be radical 3 times that 1 minus y over 2. Okay, if you don't remember that, you can, let's call this h first. So h over 1 minus y over 2, that is equals to tangent 60 degrees, right? Which is radical 3. Okay, so h is radical 3 times 1 minus y over 2. I hope you see that. Okay, so this height here is radical 3 times 1 minus y over 2. Therefore, the area of that triangle as a function of y will be 1/2 times the base times the height. Okay, which if we simplify, let's see, I want you to be able to see this. This guy 1/2 times another 1/2 is 1/4 times radical 3 will give us radical 3 over 4 times this guy times this guy is 1 minus y squared, right? So the volume is equal to radical 3 over 4 integral from 0 to 1 for the y of 1 minus y squared dy. Okay, I think the answer will be 1/3 of, so the answer will be, check my computation though, but I might be wrong, but there will be square root of 3 over 4 times 1/3. Okay, but yeah, check my computation. Okay, lastly, number 72. So we have the last 3 questions are questions where it is the solid is not a revolution with respect to any axis. It's just like they tell us, well, the cross section is a square, the cross section is equilateral triangle, and this one here is something else. The base of solid S is the region enclosed by y equals to 2 minus x squared and x-axis. This is x-axis. This is y-axis. 2 minus x squared looks like approximately like this. Okay, so if I kind of like continue the drawing, yeah, so this is what it looks like. Now, however, the cross section perpendicular to the y-axis, the cross section perpendicular to the y-axis, let me pick this one here, is a quarter circle. So if I pick this guy here, it gives me this quarter circle. Okay, but that means I need to integrate with respect to y. My integration later on between y equals to 0 to y equals to 2. Okay, I need to solve for x here. y equals to 2 minus x squared means x squared equals to 2 minus y. X is plus minus square root of 2 minus y. So the length of this part here, you see, this is square root of 2 minus y squared. Maybe enlarge that, sorry. While the length here is 2 square root of y squared, square root of 2 minus y squared, this is negative square root of 2 minus y squared, the position here. Okay, so altogether, that will be twice, the length will be twice of that square root thingy. What I want to say is the length, the position here is square root of 2 minus y squared. Okay, this part here, the position here is negative square root of 2 minus y squared. So altogether the length will be 2 square root of 2 minus y squared. That's the radius of the quarter circle. Okay, so this is 2 square root of 2 minus y squared. Yeah, try to follow me in writing. Okay, so this guy, let me highlight so that you know which one we are working on. This guy here is now here. Okay, so the area of that quarter circle as a function of y will be 1/4 pi r squared. But the r is 2 square root of 2 minus y squared. That is 1/4 pi times 4 times 2 minus y squared. Okay, the 4 cancels, so we have the area of that quarter circle is pi times 2 minus y squared. The volume, therefore, pi times integral from 0 to 2, right? From y equals to 0 to y equals to 2 of 2 minus y squared dy. Okay, again, my assumption, you must be able to integrate that yourself. Okay, I hope these examples here are good enough for you. If my explanation is not clear, okay, slow down, try to do it on your own, right? But you will see the principle always start with sketch the domain, okay, and then when you do the cross section, see what happened, what the cross section look like, so that you can find the area of that cross section before you get into the integral for the volume. That procedures, those 4 steps, is being applied in each one of my question here. The domain of integration, do the cross section, see what it looks like, get the measurements so that we can find the area of that cross section, and then we set up the integral for the volume, right? Okay, this is the solid, the domain of integration, the shape of the cross section, find the area, and then set up the integral for the volume. That is consistently done for every one of these questions. Number 24, I think, is on the hard side. You know, the integration. You know, it's doable though. It's still doable. It's just like, wow. Okay, this is where I'm gonna stop.